Welcome to Lab Activity 4, Discrete Random Variables, Part B, where we cover the Bernoulli and the binomial distribution. Now this entire lab activity is about discrete random variables. In the previous part, Part A, it dealt with the unnamed ones that can be summarized in a short table. This part to the lab activity is going to cover the Bernoulli and the binomial distributions. And technically the Bernoulli distribution is just a special case of the binomial. Alternatively, the binomial can be thought of as just a generalization of the Bernoulli. So we got three objectives for this lab. Be able to plot a binomial probability function, both the probability mass function and the cumulative distribution function. Be able to draw a random sample from this distribution, and to be able to determine the likeliness of certain claimed outcomes. And that last one is actually going to be the link, or a link, between this probability part of Chapter 4 and the statistics part of Chapters 5, 6, 7, 8, all the way up to 12. So again, Activity 4, start R, all the fun stuff that we always do. Set the working directory. Try to figure out where my working directory is. Stat methods, lab activities, activity 4, open, just to double check, dir, open close parents. Ooh, lab4a.r. Did you remember to save the script from lab4a? I hope so. So on your own or in your imagination or have your significant other or your children if you've got children or your golden retriever if you don't have children, flip a coin 14 times and assume the coin is fair. Did you get exactly 7 heads? Probably not. The reason behind the number of observed heads not always being what we expect is that flipping a coin is a random action. The number of heads flipped is a random variable. We do not know its outcome until we actually perform the experiment or collect the data or whatever you want to call it. So random variables are about things that are going to happen in the future, almost always. If there's an inherent variation in the outcomes, which is reality, then how can we possibly test if a coin is fair? Were I to flip a coin 4 times and have heads come up all 4 times, is the coin fair? Is it weighted? Perhaps. I don't know. But we do know something. We do know that there's a 1 in 8 chance, a 12.5% chance, that a fair coin flipped 4 times will come up either all heads or all tails. Now stop there for a second. I flipped a coin that came up 4 times heads. Why is it that all of a sudden I'm talking about 4 heads or 4 tails? That's very important for the future. Hit the pause button, think about it for a bit, then hit the play button and let's continue. Is that enough evidence for us to conclude the coin is unfair? No, not really. The outcome is common enough. So what if we flip heads 100 times in a row? Is it still possible the coin is fair? Absolutely. It's unlikely. The probability is about 7 times 10 to the negative 31, which means if we were to do it every second from the beginning of time, we still wouldn't have 100 times in a row, but it's still a non-zero probability. It's still possible. It's not likely, but it is still possible. So we would conclude in that case, if I flip 100 heads in a row, we would conclude that there is overwhelming evidence the coin is unfair. And I do really need to emphasize this point. It's overwhelming evidence. It's not proof. It is still possible the coin is fair. But I'm willing to bet every dollar in my wallet that it's not. All one of them. So there has to be, between those two extremes, there has to be some sort of boundary between the two possible conclusions. The Yeah, that's reasonable, and the no, that is completely unreasonable. And we actually, in the social sciences and in most sciences out there, there are exceptions, of course, set that point at 5%. If the data we observe has less than a 5% probability of happening by chance, or something more extreme than what we observe, we conclude that there is sufficient evidence to reject the null hypothesis. And let's go ahead and hit pause and remember that last sentence. In terms of coin flipping, flipping all heads or all tails in 5 flips of the coin will happen about 6.25% of the time. In 6 flips, about 3.125% of the time. Thus, if we flip a coin 6 times and it comes up all heads or all tails, we can therefore conclude that there is sufficient evidence that the coin is not fair. So where did I get those numbers? From R. Number of heads flipped is a random variable, follows a binomial distribution. If we define y as the number of times I flip the head in n flips of a coin, y is distributed binomial n pi. The Bernoulli distribution is just a binomial with n equal 1. There are several R functions to help us with the binomial distribution. All have the root of binom. All 4 require a prefix to that root. To calculate the probability of a single outcome, use the prefix d. So let me go ahead, new script, tile vertically. If I would like to calculate the probability of getting exactly 6 heads, while flipping a coin 10 times, and that coin, by the way, is fair, that probability is going to be 0.25. If I would like to calculate the probability that you got exactly, if we go back to the beginning of this part of the lab activity, if you got exactly 7 heads in 14 flips of a fair coin, the probability of that happening is about 1 in 5. It's unlikely, but it is the most likely outcome. If I would like to calculate the probability of exactly, and the d comes from the exactly part, and we are talking about a binomial random variable, exactly 5 heads in 5 flips of a coin where that coin is fair, that probability is about 3%. That is, the probability of getting all heads in 5 flips of a fair coin is about 3%. If I want to calculate the probability, if I want to know the probability of getting 5 heads or 5 tails in 5 flips of a coin, of a fair coin, notice if we have 5 heads, that we have 0 tails. That probability is 6.25%. If I flip 5 heads, I flip 0 tails. Next, if I flip a coin 20 times and got 4 heads, is the coin fair? Well, let's find out. Long line. Notice I'm going to break it after the plus sign. I'm going to indent it just so that I can read it better. I would like to know if I flip the coin 20 times and got 4 heads, these 5 are the probability that the number of heads is 0, or 1, or 2, or 3, or 4. These 5 are the probability that the number of tails is 0, or 1, or 2, or 3, or 4. Altogether, this is going to be the probability that I get 4 heads or 4 tails. And it's about 1.2%. Because 1.2% is less than 5%, we reject the claim that the coin is fair. Now we actually can simplify that. The D binomial is for calculating the probability that the random variable is equal to a specified value. P binomial is the probability that the random variable is less than or equal to a specific value. So P binomial of 4, comma, prob equals 0.5, comma, size equals 20. That line is the probability that I get 0, 1, 2, 3, or 4 heads from 20 flips of a fair coin. Now I can double that if I wished, 2 times that, to get the probability of getting 0, 1, 2, 3, 4 heads, or 0, 1, 2, 3, or 4 tails. And that number looks very familiar, the 1.2%. Again, 1.2% is less than alpha, 0.05. Therefore, we conclude that the evidence is against the claim that the coin is fair. The p binomial function returns the cumulative probability, not the point probability. So step 2D shows us how to calculate some very important probabilities. For instance, I want to calculate the probability that x is less than or equal to 8. Because it's less than or equal to, I'm going to do p. Because x has a binomial distribution, I'm going to do p binom. Because I want to find the probability that x is less than or equal to 8, it's going to be p binom of 8. Because x is distributed binomial with size of 10 and probability of 35%, p binom 8 comma size equals 10 comma prob equals 0.35 will give us the probability of having 8 or fewer heads on an unfairly weighted coin flipped 10 times. And that unfairly weighted is 35% chance of getting a head. If I want to know the probability of getting 1 or fewer, the only thing I need to change is that 8 to a 1. 8.595444% chance of getting 1 or fewer heads under those conditions. If I would like to know the probability of getting 4 or more, we note that the p prefix only gives us the less than or equal to. So we need to change the x is greater than or equal to 4 into some sort of less than or equal to. So this would be p binom, and greater than or equal to 4 is the same as less than or equal to 3. Again, size equals 10, prob equals 0.35. About 48.6% chance. Say that probability x is between 10 and 18 inclusive. So that's going to be the probability that x is less than or equal to 18. prob minus the probability x is less than or equal to 9. Hit pause, rethink what I just said. Probability that x is between 18 and 10 inclusive is the same as the probability x is less than or equal to 18 minus the probability that x is less than or equal to 9. Pretty darn small number. Next question, what does the binomial 10 1/2 distribution look like? I'll let you copy the things in. It looks like that. It's symmetric. Because p is equal to 1/2, the binomial distribution is going to be symmetric. In general, the binomial distribution will not be symmetric. It's symmetric only when the success probability is 1/2. So what does the cumulative distribution function look like? It looks like that. Again, notice that it is non-decreasing. Starts at 0, eventually ends up at 1. Cumulative distributions is a probability that the random variable is less than or equal to a specific value. Cumulative distributions will be much more important when we talk about continuous random variables. If you want to find the median, it's going to be handy to throw in an AB line horizontal of 0.5. The first point where the cumulative distribution function is greater than or equal to 1/2 happens here at y equals 5, which means that 5 is the median. Part 3, or section 3, or step 3, we're going to estimate some probabilities and parameters of the binomial using randomness. Let's suppose we flip a coin, a fair coin, 1,000 times. What's the expected number of heads? What's the standard deviation of that estimate? If we actually did this and got 418 heads, do we have sufficient evidence that the coin is unfair? We can do all of that exactly. If not now, then at some point in the future. We're going to first do this as simulating flipping a coin 1,000 times. Now let's look at this. R for random draws or for simulation. Binom because we're doing this from a binomial distribution. We're doing it to one coin. It's a fair coin, so the probability of a head or probability of a success is 1/2. And we're going to flip that one coin 1,000 times. So this is going to be the outcome of one experiment of me flipping one coin 1,000 times. And voila, I did it. I got 504 heads. Now, if you want to agree with me on this, go ahead and set the seed. I don't like 3. I'm going to set it to 9. We run those two lines, all of us will get 510 heads. What will we get if we run those two lines again? Yes, 510 heads. But wait, what if we run them a third time? Yes, 510. Now, the next question is, I want to simulate 1,000 such experiments. Not just one experiment of me flipping it 1,000 times, but 1,000,000 or 1,000,000,000 or a quadrillion times I'm running this experiment. All we have to do is change that 1 to however many times we want to do the experiment. So instead of flipping one coin 1,000 times, I could flip 10 coins 1,000 times and look at the number of heads for each of those coins. I could flip 100 coins 1,000 times and look at the number of heads for each of those. Let's go back to the 10 because we can actually see 10. So this line will tell me, or I'm going to run both of these so we all agree. So that tells me that in the first time that I flip the coin 1,000 times, or flip the first coin 1,000 times, I get 510 heads. The second coin I flip 1,000 times, I get 503 heads. The third coin I flip 1,000 times, I get 516 heads. The fourth coin, etc. Now I can actually do this 1,000,000 times, or do it 1,000 times to 1,000,000 coins. And voila, there we go, or at least a lot of them. So the 99,982nd coin that I flipped 1,000 times, I got 501 hits. Notice the randomness. That's because coins and the heads that come up are random variables. Now I could estimate the expected number of heads I get. I could also estimate what's called a 95% confidence interval for those. So let's first of all estimate the average number of heads in 1,000 flips of the coin. I'm going to save this line as a variable, call it OBS for no reason. And I want to find the average, so it's going to be the mean of OBS. Run those three, 499.9842. Huh, that's not surprising. We know the expected value of a binomial random variable is n times p is 1,000 times 1/2 is 500. So we got pretty close just by doing this randomly. Now if I want to get a 95%, what's called a 95% confidence interval, I'm going to use the quantile function. The first slot goes to the variable, second slot goes to the percentiles that I want to calculate for. Those two percentiles that I want to calculate for are the 2.5th percentile and the 97.5th percentile. Because if you look at this, 97.5% minus 2.5% is equal to 95%. And remember where we start to reject things, it's at 5%. 100% minus 5% is at 95%, and we're taking that 95% chunk out of the middle, which leaves 2.5% on each end. So I'm 95% confident that the total number, assuming that the coin is fair, that I will get somewhere between 469 and 531 inclusive heads on those 1,000 flips of the coin. Which means if I've got a coin and I flip it and I come up at 450 heads, I've got sufficient evidence that the coin is not fair. At least in terms of how we're defining sufficient evidence. The flip side of this is that if I flip the coin 1,000 times and do that experiment a gazillion times, 95% of the time I'm going to conclude that I don't have a fair coin, even if I do. But we've got to draw the line somewhere. And so with a nod towards the legal system, where we need overwhelming evidence, we're going to draw the line at 5%. It is what it has to be. We have to draw that line somewhere. Now we could directly calculate, and I always encourage direct calculations if possible. We could directly calculate those endpoints of the confidence interval. And we'll do it using the Q prefix, Q for quantile, for the binomial. What are those two endpoints that I want? What are those two percentiles? The same as before. But since we're doing it for the binomial, we have to specify the parameters of this binomial. We're flipping the coin 1,000 times. If I can type. And we're hypothesizing that the coin is fair. So calculating it exactly, The 95% confidence interval is from 469 to 531 inclusive, which surprisingly, or maybe not surprisingly, is exactly what we got from our estimation. Now, if you're not entirely sure how flipping coins applies to your research, join the club. But a lot of things in this world are heads and tails, success and fail, A and B. For instance, the ratio of males to females in Tulsa. We can use binomial because there's two possible outcomes. Proportion of people supporting a specific candidate. Two possible outcomes. They support the candidate, they don't support the candidate. Smokers, they smoke, they don't smoke. Red M&Ms, it's a red M&M, it's not red M&M. Notice two possible outcomes. A success, something that we define as a success, and a failure. The proportion that are freshmen. Freshmen versus not freshmen. Proportion that are Christian. Christian versus not Christian. Etc., etc. Almost every single, in fact, I'm going to say every single, not the almost, every single categorical variable can be framed in terms of proportions or several proportions put together, meaningfully framed in those terms. Continuous variables may not be able to be meaningfully framed in those terms, but also can't always be framed there. So I'll let you work through the M&Ms part, and let me just bring this to a conclusion. So in this activity, we covered the binomial distribution. And technically, we also covered the Bernoulli distribution, which is just a special case of the binomial. We saw a graphic of the probability mass function. We also know how to do cumulative distribution functions for the binomial. We calculated some probabilities. We were introduced to p-values and confidence intervals, two concepts that are going to be extremely important in the final half of the course. In part 3, or part C, depending on how I numbered these, of this lab activity, we're going to cover the geometric distribution. Before you move on to part C, go back over the handout on what makes a binomial distribution. Make sure you understand the 5 requirements, because the geometric distribution violates one or more of those. And you need to know when a distribution is going to be a geometric distribution and when it's going to be a binomial. So I hope this was helpful. Take care of yourself.